Martin.
Thank you, David. I know we're running a little behind. I'll see if I can catch a tailwind. I'd like to acknowledge my co-authors and co-conspirators here, Sarah and Catherine. We've been working on this project off and on for a while. So let's dive right in here. So the looming issue, right, is that salt marsh persistence, we know and we've heard from several talks, several great models that we've seen, is dependent on plants to both trap sediment and then to contribute organic matter towards accretion. So the question here, of course, is with 21st century sea level rise, get that going. If it's greater than the wetland soil formation process, then even though we've created this habitat through inundation, will the plants and animals actually be able to migrate in there? In other words, will the pH, the salinity, these kinds of things be conducive to their actually being there? And if not, of course, this might create extensive networks of unique habitat that translates to invasive species, right? Well, so the idea would be to have a crystal ball and find out what the soil conditions look like 50 years, 100 years in the future. We don't have that, but we have all these wonderful dike removals that are taking place. So we got the idea that I know a dike removal is rapid sea level rise by beyond explanation, but on the other hand, it does maybe give us some idea about trends that might be taking place that we could take a look at. So we went down to the Coquille estuary, and there's the Nelleston Marsh and the Bandon Marsh. And here is Nelleston prior to dike removal, and then this is immediately, well, somewhat within a few days after dike removal. And again, to my point about rapid sea level rise, this is a significant tide, but the entire area is not underwater. So the entire estuary, even though it's been restored, isn't flooding the whole thing every day, just like every other estuary. Here's the reference marsh, Bandon, under another pretty significant tide. So what we did, we just wanted to find out what the soil conditions were like. So we went out there and we said, okay, we want to be able to kind of project this onto different elevations. So we start in the high marsh, and then we start surveying, and every decrease of 10 centimeters in elevation, we stop, put in a sample point, and Sarah does the vegetation analysis, and then Catherine does the soil fauna, which they can report on next year. I'll drag them out to Boise. And then I work on the soil. And there's a lot of soil stuff we look at, but the stuff I want to report today is moisture, salinity, pH organic matter, and ORP, oxidation reduction potential, because these are the adaphic factors that are important to plants in order for them to move into a new environment. And then these things down here are kind of important for nutrient cycling and carbon sequestration, those sorts of things. So here is Coquille estuary. Here's our two transects that we put in. So this is in the, we went in 1 year after dike removal, and then went again 2 years after dike removal, and then also the same years in the reference marsh there. So this is what it looks like in the reference marsh. This is kind of transitional upland vegetation going down into the high marsh. Here is the, if you've ever been on a marsh, the incredibly flat high marsh plateau where there's virtually no change in elevation, and sometimes a monoculture. And then the transition down into low marsh and finally into mudflats. So this is our 10 centimeter spacing that you see there. And then we also went to the Salmon River estuary, where there's been ongoing restoration since the late 1970s. And they've had a series of dike removals in 1978, 86, and 96, and then more recently, so about every 11 years, they remove a dike. So we did the same thing, put in a transect in the 1978 removal, and then the restoration so that we could look at roughly 40 years since dike removal. So we have 1 year, 2 year, 40 years, kind of the idea there. And if you spend any time with wetland soils, this will look incredibly familiar. Here's the upper 5 centimeters that we use for analysis. And we have lots of different ways to sample, but there's that great redoxomorphic condition that we love to talk about. So the reddening there from oxidation, and then the black from the reduction. So these are aerobic, anaerobic soils that are classic wetland soils, right? All right, so we'll jump into some results and some really simple graphs. I need simple graphs. So an upper graph here, this is Coquille River, so this is the Bandon site, and this is soil moisture. And in the blue is the 1 year after restoration, and then the kind of the orange there, rust, I like rust, is 2 years after restoration, and then there's our reference marsh. And I should point out that we don't have data for, well, we have data for the lower part of the transect for the first year, but Faze Creek decided to hang a right, and it wiped out the lower transect. So it's not comparable to year 2 anymore, so we just use the upper portion there. But nevertheless, so we look at soil moisture. So soil moisture is important. If you're going to have anaerobic conditions, you have to have wet soil. So 1 year after dike removal, there's quite a bit of variability in the blue there, but nevertheless, it's significantly wet even in the high marsh area. And by 2 years, it's pretty indistinguishable. So we can say that at least within a year to 2 years after dike removal, you have conditions that are suitable for anaerobic soils. In other words, the soils are wet more than 2 weeks out of the year. Salmon River, same thing. 40 years, it's indistinguishable in terms of soil moisture between the dike removal and then the reference condition. We look at salinity, on the other hand. 1 year after dike removal, it's nowhere close to a reference condition. And the folks down at Bandon had a group go down and do some pre-dike removal soil, just a little bit of soil work. We weren't on board quite at that time, so I matched up their one soil data point that matches the elevation of our transect at that particular point. So some of these data have before dike removal. So you can see before dike removal, very low salinity in the Nalestin area. And then 1 year after removal, the salinity jumps up a little bit, but still not, again, near restoration. And then interestingly, you start to see by year 2, you're getting conditions that are pretty close to reference condition. And this one's kind of fun. Every now and then you run into a marsh where there's a natural levee. So the salinity actually increases on the backside of the levee. So it's not, this doesn't happen at salmon. Salmon has kind of your classic increases in salinity as you go up into the reference marsh. Up in elevation here. So higher elevation, lower elevation. So nevertheless, 2 years following removal, salinity is kind of on board. And of course, same thing, 40 years after removal, salinity looks pretty good. And then we get into pH, so a little bit more into what plant tolerant or tolerances might be. 1 year following dike removal, and there's the before dike removal, really acidic conditions. And we find this everywhere we go in all these dike removal sites. If you get there beforehand, we've got pH levels of 3.7, 3.8, because again, estuaries store sulfides, and then those sulfides will sit there forever, hopefully. But if you remove the water source, then they will oxidize to sulfuric acid, and you have acid sulfate soil. So pH down here about 4. So 1 year after dike removal, you still have extremely acid conditions. 2 years after dike removal, though, we're starting to get close to reference. So this was pretty surprising, pretty interesting. But still high variability in that pH, and nowhere near kind of the classic linear distribution. And then this starts to get interesting. Salmon River, so 40 years after dike removal, and you're not getting a great fit necessarily on pH. It's actually a little more alkaline down here in the mudflats, low marsh, and then actually still more acidic. So again, that idea about it was probably at 4, and 40 years later it's gone up about a point and a half, but not quite into that mid-6 range that we would want for up there in the higher marsh. And then organic matter. Of course, organic matter is important because we're going to build marshes. We have to store organic matter. Organic matter was really low in the pre-dike era because, again, it's all oxidizing. Well, it's been behind the dikes. 1 year after dike removal, you're starting to get an increase in organic matter. And actually, you have the highest organic matter because this is an area of these really thick sedges that they had there, and they hadn't died yet. So this is still quite a bit of organics that was left over from that patch. Year 2, these are the sedges again. They've died at this point, but they're still decaying. So one reason you have high organic matter here, this is actually the fast carbon. This isn't the slow carbon that we want to store necessarily. So we should see this continue to decrease. But down here in the low marsh, everything's kind of on target after 2 years. And then, interestingly, Salmon River, again, 40 years after, the trend is there in terms of increasing organic matter as you move up into the high marsh, as we'd expect. But it still is, and this is if you do a t-test, it's significantly lower than the reference condition. So 40 years later, we're not at the sort of optimum organic matter storage in the dike removal that we are in the reference condition. And then ORP. The reason I do ORP is that there are a lot of ecosystem services associated with wetlands and salt marshes, things like nutrient cycling and carbon sequestration. But in order for those things to happen, you have to have a pretty reduced state in your soil. So ORP is a measurement of how reduced the soil is. So we measure it in millivolts, and what you'll see if you were to inundate a soil is that once the EH drops down to about 330, then all the oxygen is gone, and then it kind of works its way down. We lose the nitrogen, then the manganese, iron, this goes to sulfate, and then the methane gets stored as carbon. So in order to have things like, storage of sulfides, to have denitrification and these sorts of things, you need to get down here in these low ORP numbers. Coquille River, really high ORP, but it's all kind of high in the high area. But still relatively high ORP after 2 years. And same thing, after 40 years, we still have ORP that's significantly higher than a reference condition. Again, probably indicating that there isn't enough organic matter there for these processes to bring down the ORP. All right, so where does that put us? Current status in molestin, soil moisture and salinity are similar to the reference marsh. pH is close in the low marsh, but still more acidic in the high marsh. Organic matter percentage is trending, but still different, and ORP is still higher. We flip over there to salmon. Soil moisture, salinity, pH, they're all at reference. Organic matter, similar trend, but is still lower, and ORP is still higher. So I want to talk really briefly about the persistence of human disturbance. Can everyone in the room pick out the 1986 dike in this picture without my little red line pointed out there? So this is just stock photo here, right? This is wetland vegetation. It's just different than that wetland vegetation. And some people from Oregon State, a couple dissertations came out in the 90s, and they estimated it would take about 50 years for the vegetation to return to a reference vegetation. So that's about 10 years from now, if we get there. So what are some implications for sea level rise? Well, one is that relatively small increases in elevation in sea level, like 10 centimeters, will necessitate a change in vegetation. So there's very steep gradients here and big changes that take place. But that hasn't already occurred in 40 years. These transects only span 1.5 meters elevation, and yet you have huge differences, right? 1% to 60% organic matter. So if, with 40 to 50 centimeters of sea level rise, that's a huge shift in those kinds of conditions in organic matter. And the other piece is these transitions from high marsh to low marsh to mudflat are really abrupt, and I'll show you what I mean by that. There's my little tiny transect. So this is the entire 1.5 meter of elevation right there. I threw in another one there just to be sure. This entire platform only differs in 5 centimeters from that point. So what that indicates is with about 50 centimeters of sea level rise, this whole area is inundated. Now, if it happens slowly enough, right? Well, a couple pictures here of that area. So there's low tide, there's high tide. Again, this is a high tide, it's not a big high tide. And there's a soil core showing the earthquake. I can talk about that later if you want, it's fun. So the idea is, at the current rate of sea level rise, we should persist. If it's a little faster than now, 40 to 50 centimeters of sea level rise, we could inundate that entire high marsh, and then of course it'll convert to low marsh, which again, from an ecosystem services standpoint, what does that mean? Well, it means things that we're probably going to lose some high marsh and gain some low marsh, and that means that organic matter accumulation is going to decrease because it's lower in the low marsh. And if we combine that with relatively high ORP, right, if there's this lag, 50-year lag in ORP, then there's going to be potentially lower carbon storage and lower nutrient retention. And then the other piece, our C3 vegetation, which thrives in the high CO2 environment, happens to be something that you find in the high marsh, which is going to be on the ebb. And then the C4 is our low marsh vegetation, thrives in relatively low conditions, but we'll have lots of low marsh. There's a bit of a paradox there. But this brings me to the role of dike removal. The role of dike removal in sea level rise is, yeah, it's not a perfect fix, even after maybe several decades, but it certainly trends in the right direction, and we get some ecosystem services out of dike removals. So if you want to, and if we are at the same time losing regular, areas that aren't diked currently to sea level rise, then maybe we have a no net loss. I hate to say no net loss, but a no net loss indication by the dike removal process. So at least shows us some idea about when it might be working. Thanks.
Martin. So we do have time for questions. We have any?
End of the conference.
There's one there. You want to yell out? Yeah.
Pardon me?
So
no, lots of other people are measuring accretion rates.
So look, the question was about accretion rates, just for the tape there.
No, so we don't have set tables or any of that kind of stuff out there. We're kind of relying on Kevin to do all that for us. But, No, we'd love to do that. We're focusing on the physiochemical properties, and what we're really going at, if Sarah and Kat were here, is we're trying to figure out the plant-soil fauna interactions and really define those for the tide flat, low marsh, and the high marsh, so that as these models come together and we say, well, this area is going to be high marsh, we can say, well, this is what you should expect to find. So.
Questions? Well, if not, thank you everyone for attending, and thank you to our speakers. And I believe the plenary session downstairs, a couple great talks, so everyone stick around, I hope. Starts at 3-4, oh, it's right here. Oh, okay, I'm sorry. That's right, it's in this room, and it starts at 3:45 if we stay on schedule. So thank you a lot.